alternating series, and absolute convergence. Consider the following series. Here we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, which can be summarized by the summation n equals 1 to infinity, -1 to the n minus 1 times 1 over n. Notice that this is an alternating series because every other term alternates from positive to negative, back to positive, back to negative, etc. The second series is also an alternating series. The second series starts off negative and then goes positive and then negative, positive, negative, etc. An alternating series that satisfies these two conditions is always convergent. This is the alternating series test. The two conditions are that Bn plus 1 has to be less than or equal to Bn for all n. Or a more simple way of saying this is that Bn has to be non-increasing, or decreasing will do. And the second condition is the limit of Bn is equal to 0. So anytime you have an alternating series that satisfies these two conditions, the series must be convergent. As an example, let's consider the alternating harmonic series. Here we have the series 1 minus 1/2 plus 1/3 minus 1/4, etc. This is the alternating version of the harmonic series. And we know that the harmonic series is a series that diverges. How about the alternating harmonic series? Well, first of all, let's identify that Bn for this series is 1 over n. So let's remember that when you have an alternating series, we have our alternating factor, which in this case is -1 to the n minus 1. And I just want to say that it can also be written as -1 to the n plus 1. Different books will use different notations, but in this case we have -1 to the n minus 1. And then divided by n is the same as multiplying by 1 over n. N equals 1 to infinity. This portion is your Bn. So Bn is the part of the term except for the alternating factor. So first of all, I want to point out that this is non-increasing, right? As n gets bigger, 1 over n does not increase. In fact, it decreases. And we can actually prove this by looking at the function f of x equals 1 over x, which we know has a derivative of -1 divided by x squared, and that is always a negative number, and that means that f of x is decreasing. And if the function 1 over x is decreasing, then the function 1 over n is also decreasing. So we've shown that the first condition of the alternating series test is satisfied. And the second condition is that when we take the limit as n goes to infinity of Bn, we get 0. And that is obviously true as well. Therefore, we can say this series converges by the alternating series test. In the next example, we have a series here which is alternating, but it does not converge. And the reason for this is, I'm just going to jump to the second condition. If I identify Bn here as 3n over 4n minus 1, if we take the limit as n goes to infinity of this Bn, we end up getting 3/4, and 3/4 is not 0. So the alternating series test gives no conclusion here. However, if I take the limit as n goes to infinity of the entire nth term, which is going to be the inclusion of the alternating factor, well, we know that this limit is 3/4. So when we put in the alternating factor, this is going to make this limit not exist, because basically the odd terms, the odd powered terms, are going to go to negative 3/4, and the even powered terms are going to go to positive 3/4. And so this limit does not exist. Well, if the limit of the nth term does not exist, we know that this series is therefore divergent. But it's not from the alternating series test. It's by the divergence test. In our next example, we want to test this series for convergence or divergence using the alternating series test. So let's point out that Bn is equal to n squared divided by n cubed plus 1. So is this decreasing? Well, let's check. Let's define the function f of x to be x squared over x cubed plus 1. We'll take the derivative using the quotient rule. That's x cubed plus 1 times 2x minus x squared times 3x squared, all divided by the bottom function squared. Simplifying here, we have 2x to the fourth plus 2x minus 3x to the fourth divided by the same thing. And this is 2x minus x to the fourth divided by the same thing. And in the numerator, if I factor out an x, we get x times 2 minus x cubed over x cubed plus 1 squared. And this is going to be less than 0 as long as we plug in a value of x that is bigger than 1, right? And the reason is because if x is positive, this is always positive, this is positive, but if you plug in a number bigger than 1, 2 take away x cubed is going to be a negative number. So we have shown that the derivative is negative, and this means the function is decreasing. So we have shown the first part of the alternating series test. The second part, we need to take the limit as n goes to infinity of n squared over n cubed plus 1. Of course, this limit is infinity over infinity. But we can apply L'Hopital's rule. And if we do this, we have 2n over 3n squared. And from here, we can cancel out a factor of n. And this becomes the limit of 2 divided by 3n as n goes to infinity. And this limit is clearly 0. And so because it satisfies these two conditions, we know that this series converges by the alternating series test. We have an alternating series estimation theorem, which is very easy to use. It says if you have a converging alternating series that has a sum equal to s, then the error when you add up the first n terms, so the nth partial sum, is always going to be less than or equal to the next term of the series. So as an example, let's find the sum of the series here correct to 3 decimal places. The first thing we need to do is determine how many terms do we have to add up to ensure that we have 3 decimal places of accuracy. Well, let's talk about what we need for 3 decimal places of accuracy. We need the error to be less than 0.0005. So notice for 3 decimal places of accuracy, I need the 4th decimal place here to be less than 5. So how do we do this? Well, we know that the absolute value of the sum minus the nth partial sum is always less than or equal to the n plus 1 term, and we need this to be less than 0.0005. So what is the n plus 1 term? Well, first, let's say, what is Bn? Again, Bn is just the non-alternating part of this, and so it is 1 over n factorial. And this means that Bn plus 1 is 1 over n plus 1 factorial. And we need this to be less than 0.0005. Well, it's a little bit easier to think about if you change this into a fraction. So we have 1 over n plus 1 factorial is less than, this is the tenths, hundredths, thousandths, 10,000ths place. So this is 5 over 10,000, which is the same as 1 over 2,000. And if you take the reciprocal of both sides, you get n plus 1 factorial must be greater than 2,000. So remember, when you take reciprocals of positive numbers, the inequality reverses. So now we have to figure out what is the first value of n that makes this true. And we're just going to do this by inspection. Now, I won't start with a super low value of n. What if I tried n equals 4? What would we get here if we plugged in n equals 4? Well, we would get 4 plus 1 factorial, which is 5 factorial. And that's 5 times 4 times 3 times 2 times 1, which is 120. Well, that's not bigger than 2,000, is it? So let's try n equals 5. If I plug in 5, I get 5 plus 1 factorial, which is 6 factorial, which ends up being 720. Again, 720 is still not bigger than 2,000. So let's try n equals 6. We get 6 plus 1 factorial, which is 7 factorial, and 7 factorial turns out to be 5,040. And so this is the one here, because 5,040 is greater than 2,000. So what partial sum do we need to add up to ensure that our error is less than 0.0005? Well, remember, it was n equals 6 that gave us this. So we need to find the sixth partial sum. And the sixth partial sum means we are going to add from n equals 0 to 6. So whatever you find here for the value of n, that tells you where you're going to stop. It actually doesn't always coincide with the number of terms you're going to add up. So in this case, when you add from 0 to 6, you're actually adding up 7 terms, but it tells you where to stop. And so we're going to add from 0 to 6, negative 1 to the n over n factorial. Let's go ahead and plug in n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and finally n equals 6. And then you would probably want to do this on a calculator. And so I'll go ahead and bring in the result here. And when you add this up and round it to 3 decimal places, we get 0.368. So this alternating series estimation theorem is very simple to use. Next, let's talk about absolute convergence and conditional convergence. So first of all, if we're given any series summation of an, we can consider the corresponding series where we take the absolute value of every term an. And that would result in the absolute value of a1 plus the absolute value of a2 plus the absolute value of a3, etc. So we are simply taking the absolute value of every term of the original series. So this, of course, is always going to be a positive term series, even if the original values of an may have been negative. So the definition is, we say a series, summation an, is absolutely convergent if the sum of the absolute values is also convergent. Note that if a series already has positive terms, then the sum of the absolute value is the same as the original series. And then the absolute convergence would be the same as regular convergence in this case. So it's really only interesting to talk about absolute convergence for series that have some positive terms and some negative terms. For example, the alternating series that you see here, summation n equals 1 to infinity, negative 1 to the n minus 1 divided by n squared, which is an alternating series, 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, etc. This series is convergent by the alternating series test. Okay, I won't prove this here, but you can run the alternating series test on this and show that this converges. But just because it converges does not mean that it converges absolutely. So we still have the question, but is it absolutely convergent? Well, to do this, we have to take the sum of the series where we take the absolute value of every term of that series. Well, let's think about this. When you take an absolute value of a fraction, that is the same as taking the absolute value of the numerator and the absolute value of the denominator. And negative 1 to the n minus 1 is just positive or negative 1. And so when you take the absolute value of that, you are always going to get 1. And n squared is already positive. So the absolute value of n squared is the same as n squared. And this is a p equals 2 p series. And when you apply the p series, if p is bigger than 1, we know that it converges. So what does this mean? Well, I took the absolute value of every term, and we got a series that still converges. So, yes, this series is absolutely convergent. Next, we have a definition for conditional convergence. A series is called conditionally convergent if it is convergent but not absolutely convergent. So, for example, the alternating harmonic series is a conditionally convergent series because we know this series converges by the alternating series test. But when you take the absolute value of each term, this series turns into the harmonic series, and we know the harmonic series diverges. So again, the alternating harmonic series converges, but when you take the absolute value of every term, you get a series that diverges. And so what that means is the original series is what we call conditionally convergent. It's only convergent on the condition that it alternates. As soon as you take away the alternating factor, it's no longer convergent. So if a series is conditionally convergent, it means that it is a weaker type of convergence. And so naturally we have a theorem that says if a series is absolutely convergent, then it is convergent. So in other words, if you take the absolute value of every term of a series and it converges, then it's going to converge without you taking the absolute value of every term. And sometimes this theorem can be useful, like in the next example. let's determine whether the following series is convergent or divergent. Well, this is a very tricky series because we have the cosine of n in the numerator and n squared in the denominator. But these values, cosine of 1, cosine of 2, cosine of 3, some of those values are positive and some of those values are negative, but it doesn't necessarily alternate from positive to negative from each term to the next. So this is a kind of strange type of series. But let's see what we know. Suppose we took that series and we took the absolute value of the nth term. Well, this would give us the series of the absolute value of the cosine of n divided by the absolute value of n squared. And we know the absolute value of n squared is the same as n squared. But on top, we still have the absolute value of the cosine of n because, again, we don't know what this is. However, we do know this about cosine. No matter what value you plug into cosine, when you take the absolute value of that, it is always going to be a number less than or equal to 1. So this series is less than or equal to the sum n equals 1 to infinity of 1 over n squared, right? Because the absolute value of cosine is always less than or equal to 1. But we know this series. This is a p equals 2, which is bigger than 1, p series, and therefore converges. Well, if this series converges, then this series has to converge, because the direct comparison test says if you have two positive term series and one series is less than another series, and if that series converges, then this one has to converge as well. So this tells us that this series converges. But because that series converges, remember this is equal to this series. So we're saying that this converges. But that is the absolute value of the original series. So what this means, ultimately, is that our original series is absolutely convergent and therefore convergent, right? Because if a series is absolutely convergent, then it is convergent. In our final example, determine whether the series is absolutely convergent, conditionally convergent, or divergent. So I'm just going to point out that the first series here converges by the alternating series test. So we can show that Bn equals 1 over n cubed is decreasing. Also, the limit as n goes to infinity of 1 over n cubed is equal to 0. In the second series, this one also converges by the alternating series test. Bn in this case is 1 divided by the cube root of n, which is decreasing. So as n gets bigger, 1 over the cube root of n gets smaller. And the limit as n goes to infinity of 1 over the cube root of n is also 0. So it satisfies both of the conditions for the alternating series test. So both of these series are convergent by the alternating series test. This last series is divergent. Okay, and we can show that it's divergent by just using the divergence test. If we take the limit as n goes to infinity of negative 1 to the n times n over 2n plus 1, notice that this portion goes to 1/2. And what you have is negative 1 to the n powered multiplied by something that is getting close to 1/2. And so this limit here does not exist because it's going to positive and negative 1/2 at the same time. And so it's a diverging limit. If the limit of the nth term is not 0, we know that the series diverges by the divergence test. Okay? So we are done with part C. This one is divergent. Now, back to parts A and B. We know both of these converge, but are they absolutely convergent? For that, we have to consider, what does the series do when you take the absolute value? So first of all, how about the sum n equals 1 to infinity of the absolute value of negative 1 to the n over n cubed? Well, this is going to be the sum n equals 1 to infinity of 1 over n cubed. And this is a p equals 3, which is greater than 1 p series, therefore converges. So when I take the absolute value of this, it still converges. So that means that this series is absolutely convergent. Now this series, same idea. If I take the sum of the absolute value we are going to get the sum of 1 over the cube root of n, and that is the same as the sum of 1 over n to the 1/3, and this is a p series with p equals 1/3, which is less than or equal to 1, therefore diverges. So what we had in part B is we had a series that converged by the alternating series test, but when I take the absolute value, I get a series that diverges. So that tells us that part B is a conditionally convergent series. So we have an example of each type here. We have an absolutely convergent series, a conditionally convergent series, and then this one was divergent from the beginning. And that concludes this video lesson.